Today's topic is operations on graph or operations of graph. First one is union of two graphs. If I consider G1 with vertex set V1 and edge set E2 is one graph, and G2 is another graph with vertex set V2 and edge set E2. Then union of G1 G2 is a graph obtained by taking union of vertex sets V1 V2 and union of edge set E1 and E2. Union of G1 G2 is another graph G3, which is written as G1 union G2, whose vertex set V3 is nothing but V1 union V2, and edge set E3 is union of E1 and E2. G3 is a graph with vertex set V3 and edge set E3, where V3 is nothing but union of V1 and V2 and edge set E3 is union of E1 and E2. Means this G3 will have the vertices of G1 and G2 and even the edges of G1 and edges of G2. If, for example, if I take this as G1, one, two, three, this as my G1, and then G2 I'll consider like this. One, three, 4. Okay, say if you want, I'll name the edges also A, B, C. Say this is B, D and E. This is my graph G2. Then G1 union G2 is, of course, it has all the vertices 1, 2, 3, 4 vertices it has. 1, 2, 3 from this graph G1 and the fourth vertex from G2. So 1, 2, 3 and 4. It should contain all the edges of G1 and G2. Vertex 1 to 2, there is an edge naming A. Then 2 to 3 there is an edge C. And then 1 to 3 there is an edge, the name B. And 1 to 3 B I have already drawn. And 1 to 4 there is an edge. And 4 to 3, 3 to 4 there is an edge. So this is G1 union G2. Next operation is intersection of two graphs. Same way, if G1 and G2 are the two graphs with the vertex at V1 E1 and V2 E2, then intersection of graph say G4 I'll name. This is nothing but G1 intersection G2, and it is obtained by taking vertex set. In the sense, see what happens is G4 is nothing but G1 intersection G2 will have vertex set V4 and edge set E4 such that it consists of those vertices and edges which are in both G1 and G2. Means V4 is nothing but V1 intersection V2 and E4 is nothing but E1 intersection E2. Okay, for the same graph, if I consider, I have to take all those vertices which are in both G1 and G2, and I have to consider those edges which are in both G1 and G2. So now if I consider vertex 1, it is in this graph also and in this also. So I'll take that, and 2 is there in this, but it is not there in G2. Therefore I should not consider that. And the vertex 3, it is there in both, and vertex 4 is only in this. So only 1 and 3 are the vertices which are in both G1 and G2. So for that example, I am writing G1 intersection G2 is, the vertex set is vertex number 1 and vertex number 3. But an edge which is common in both is only edge B. Therefore, G1, G3 is like this. Sorry. Right. Okay. Edge naming B. So for this example, G1 union G2 is this and G1 intersection G2 is this. So G1 union G2 is nothing but I am taking all those vertices and edges which are in G1 and G2. But when I take G1 intersection G2, I am considering only those vertices and edges which are in both G1 and G2. Next operation is Ringsum. Ringsum of a graph G1 and G2 is written as G1 Ringsum G2 and is a graph consisting of the vertex set V1 union V2. Say let me name this as G5, which is G1 Ringsum G2, okay, which has got a vertex set V5 and edge set E5, where V5 is a vertex set which is a union of vertex set V1 with V2, and E2 has an edge, E5 is edge set of G5. This has got the edges which are either in G1 or in G2 but not in both. Either in G1 or in G2 but not in both. In this sense, this is E5 is, I'll consider E1 union E2, but I have to remove the edges which are in both. So that can be written as E1 intersection E2. I hope you understood. Edge set for G5 is obtained by taking those edges which are in G1 or in G2, but I have to avoid the edges which are in both G1 and G2. For the same example, for the same G1, G2, I am drawing G1 Ringsum G2. I have to take all the vertices, okay, 1, 2, 3, 4. 1, 2, 3, 4. And I have to take up those edges which are either in G1 or in G2. So I have to remove the edges which are in both. So I know G1 intersection G2 is B. Just I have to remove this from union of G1 G2 so that I'll get G1 intersection G1 ringsum G2. So this will be my G1 ringsum G2. It has got an edge A, D, C and E. I just have to remove the edge which are in both G1, G2, that is edge B. It is in both G1, G2. So I have to remove that. Then I have to write A, C and E and D. So that I'll get G1 ringsum G2. Now there is, you can observe few things in this. One thing is, if I have a graph G, if I take ringsum of G with G, then I'm going to get a null graph. Ringsum is, I'm taking all union of vertices and I'm taking those edges which are either in G1 or in G2 but not in both. But when I take ringsum with itself, then I should not consider any edges. So I should consider only vertices. Only isolated vertices are there. Such graph is called a null graph. We have already studied it. This is one thing, and one more thing is G union of G is G, and this is same as G intersection G. Graph, union of graph with itself is a graph itself, and even the intersection of graph with itself is a graph. And if I take ringsum, as I mentioned, it is a null graph which contains all the vertices. They are isolated vertices, therefore the graph becomes null graph. And if G is a subgraph of G, capital G, then G ringsum with subgraph G is nothing but G minus G, which is a graph obtained by removing the edges of G from G. If you want, I'll write is a graph obtained by removing the edges of G from capital G. Okay, if G is a small g is a subgraph of capital G, then ringsum of G with G is G minus G. This is a graph which is obtained by removing the edges of a subgraph. If I have G1, G2, okay, then graph G1 union with G2, this is same as G2 union with G1, and even the ringsum also, G1 ringsum G2 is same as G2 ringsum G1. Similarly, intersection G1 intersection G2 is same as G2 intersection G1. It means that they follow commutative property. Okay, and one more thing to remember. If G1 and G2 are edge disjoint, G1 and G2 are edge disjoint, then G1 intersection G2 will be a null graph. Edge disjoint means there is no edge in common between G1 and G2. G1 and G2 are edge disjoint. Then G1 intersection G2 will be a null graph. Remember, vertices will be there. They are isolated vertices. There will not be any edges because they are edge disjoint. Therefore, G1 intersection G2 will be a null graph. If they are vertex disjoint, G1 and G2 are vertex disjoint, then G1 intersection G2 will be a empty graph. Empty graph will be empty graph because see, G1, G2 are vertex edge disjoint means there are no vertex in common. When there are no vertex in common, there won't be any edges. Of course, therefore, there will not be any graph. That means empty graph. So the next operation is decomposition of a graph. If a graph G is said to have been decomposed into two subgraphs, say G1 and G2, if G1 union G2 gives me the graph G and G1 intersection G2 is a null graph. A graph G is said to have been decomposed into two subgraphs, say G1, G2, if G1 union G2 is G and G1 intersection G2 is a null graph. Suppose I have a graph, say like this. Okay, vertex 1, 2, 3, 4, 5, 6. Okay, this is my G, graph G. I'm writing its G1, G2, which are the subgraphs. Say simple one I'll take. 1, 2, 3, 4. This is G1 and 4, 5, 6, which is G2. It's a decomposition. So here G1 union G2 gives me G and G1 intersection G2 gives me just a vertex 4. So which is a null graph, isolated vertex, therefore a null graph. I can give one more. It's a connected graph I have taken. I can even take disconnected graphs. Suppose this is one component and this is another component. Two components I have with the vertex at 1, 2, 3, 4, 5, 6, 7. This is my G, and yeah, I'll take up this as one set subgraph 1, 2, 3, that is G1, and four, 5, 6, 7. This is S. In this example, you can observe G1 union G2 gives me G and G1 intersection G2. There are no vertex in common because it's a disconnected graph. Therefore, you are going to get an empty graph. Remember one thing, if G is decomposed into two subgraphs, say G1, G2, then every edge of G is either in G1 or in G2 but not in both. However, some of vertices may occur in both, but edges either in G1 or in G2 but not in both.